you.
Ma'am, your voice is breaking.
Yes, Aleena. Is it better?
Yes, ma'am. It's better.
Okay. So we have to start with thermodynamics. And for kinetic theory, I'll provide you with the notes. So in kinetic theory, you need not write anything, but we'll have the discussion in the class itself. So after, towards the end of thermodynamics, I'll send you the notes of kinetic theory. Now let us start with thermodynamics. Basically, when the term therm comes, thermal means it is related to heat. That's what we studied in the thermal properties of matter. So the branch of physics which deals with the relationship between heat and work is called thermodynamics. So the chapter, this is all about thermodynamics. Now, system and surrounding we have discussed earlier also. So it is that part of the system that is under the thermodynamical consideration. So various kinds of systems are there. You have open, closed, insulated. Open system means it will have such a wall that will allow matter and heat to be exchanged. In closed system, only heat is exchanged, matter is not exchanged. And in insulated system, the matter, heat, both are not exchanged. That is what is meant by an insulated system. So here we have the full case of adiabatic that we'll be studying. Now, what is meant by surrounding? Everything outside the system that can have a direct impact on the system is surrounding. Means if I'm taking, let's say, example is that I'm taking a glass of water. Okay, this example is a glass of water. Now, just this glass of water is under consideration. So this will be my system. And rest anything that is present will be called as the surrounding. So in this universe, the complete system plus the complete surrounding will make up the universe. So system means like right now I'm talking about a pulley which has a mass attached to it. So that pulley mass will be my system. And rest anything that is present will be called as surrounding. So there are various thermodynamical parameters, but before that you write it till here, the introduction part of thermodynamics, then I'll tell you the parameters. Okay, is it clear?
Yes, ma'am.
Okay, write it. You have
Yes, ma'am.
completed the notes of the previous
Yes, ma'am.
part?
Yes, ma'am.
Okay. Stephen's law and one or two laws are. Wait, Alina. Let us complete that. Otherwise, if you start writing, then you'll not be able to add those things. Let us complete that. MSc, the Stephen's law was left. No, Wien's displacement law and Stephen's law. So basically, let me complete this because wherever you have written till emissivity.
Yes, ma'am.
Okay. After that, the Stephen's law and Wien's displacement law. These are two very short laws. So what's a perfectly black body? A perfectly black body is the one that absorbs completely all the radiations. Like if this is a completely or perfectly black body, whatever light rays will be entering, it won't reflect it, nor it will transmit it. It will just absorb all the rays that are falling into it. So that's what is meant by a perfectly black body. And what is Wien's displacement law? It's the product of wavelength at which maximum energy is emitted and the temperature of the black body. This is always constant. So Aleena, if two things are directly proportional, if two things product, they are constant. So what do you think? What is the relationship between them? They are inversely proportional. Okay. So
Yes, ma'am.
wavelength and temperature, they are inversely proportional. All right, so here the constant that is put is a B. B is the Wien's constant. So the constant that is put is a B. T is the temperature. This is B. B is the Wien's constant. So value of this B is 0.002829 millikelvin. Okay. So this you need
Yes.
to remember. And regarding the Stephen's law, so this is lambda m, means where the maximum energy is emitted. And when we're talking about the Stephen's law basically says that, see, the energy that is radiated is directly proportional to, so the constants are emissivity, a Stephen's constant, Stephen's-Boltzmann's constant, temperature to the power 4. So basically this says that energy is directly proportional to fourth power of the temperature. So formula is this. So if you start putting what is E, E is the energy radiated. What is this? This is the emissivity. And one thing you should know, E is equal to 1 for a perfectly black body. So if a perfectly black body is given to you, this will be 1. Straight away use the formula E is equal to sigma T to the power 4. That's it. What is this stigma? This is sigma. This sigma is Stephen's Boltzmann constant. Okay, whose value is 5.67 into 10 to the power minus 8. This is what is the entire form. And T is the temperature. This is the formula of it. Okay, E is equal to sigma T to the power 4. All right, this is how you have to remember. E is directly proportional to sigma T to the power 4. One or two questions are there. Quickly write down this, then I'll discuss the question.
None, ma'am.
Okay, see, Aleena, this question says that a spherical body with radius 12 centimeter radiates 450 watt at power 500 Kelvin. Now, if radius were halved and temperature doubled, what would be the power radiated? Now, see, the entire formula of E is area. Area will be 4 pi r square sigma T to the power 4. Okay, this is the formula of energy also. First power is given as 450 watt. Okay, this is saying what would be the power that is radiated, right? We have to find out the power. So power is 450 watt. It is given in the question. Now it is saying radius is half and the temperature is doubled. So see, if we write it like that, E1 by E2. See, this is your E1. What will be E2? 4 pi. Now radius is halved. So if radius is halved, then it will become r by 2 whole square. Sigma T to the power 4. Now temperature is getting doubled. So 2T to the power 4. This is it. So when you take the ratio of both of these, 4 pi r square sigma T to the power 4 divided by 4 pi r square, 1 4 will go up and this will be 4 into 4t to the power 4. So 144 gets cancelled. This becomes 4 times. So the new power will be 4 times. See, this was the previous one. This extra 4 is there. So 4p will be 4 into 450. That is 1800 watt. Okay, that is how you calculate the power. 4 is cancelled. Rest of it is also cancelled. This is cancelled. This cancelled. Okay, sigma also cancelled. T to the power 4. So new E2 is 4 times E1. So it will be multiplied by 4. Clear, Aleena?
Yes, ma'am.
Okay, write down this question and one more question we'll discuss.
None, ma'am.
See, this question says, how much faster does a cup of coffee cool off by 1 degree from 100 degrees Celsius? From 100 degrees Celsius, then from 30 degrees Celsius in a room at 20 degrees Celsius. Now see, energy, it's a very simple question. This is the formula. Change in the temperature we are going to take. So T to the power 4 minus T to the, like T2 and T1 to the power 4. That's it. So when you take the values of it, see, your energy, this is 100. So 100 plus 273, because you have to convert it into Kelvin. I hope you remember, you add 273 to the degree Celsius in order to make it in terms of Kelvin. Remember, Aleena? Whenever you have to convert degrees Celsius into Kelvin, you add 273. So 100 will become 373 to the power 4. See, sigma sigma will be cancelled. Minus. Then you have to the 0 degree, the 20 degree, right? 20 plus 273 will be 293. 293 to the power 4. divided by what is the temperature? This is 1, this is 30 degree. So when you add 30 to it, this will become 303 to the power 4. And what is 20 degree? 293 to the power. So like this only you have to put in the value. See, we have converted 100 to 373. So it is saying no, from 100, then from 30 degree at 20 degree. So 100 minus 20 degree, 30 degree minus 20 degree. Okay. So, but you cannot put it in degree. So we have converted into Kelvin. Remember this, whenever you have to convert Kelvin into degree Celsius into Kelvin, you add 273. When we were doing the scales of temperature, that time I told you, refer to that for this. Clear? And when you will solve, you will get the answer around 11.32. Is it clear, Aleena?
Yes, ma'am.
Okay, write this question, then we'll come back to thermodynamics.
Done, ma'am.
Aleena, did you write it or were you still writing the second question?
Written it. I've written it. Ma'am, are you speaking because you're muted?
Okay, Aleena, then write from here. This part we have discussed, the closed, open, and isolated system part. Okay, then I will come to the parameters.
Okay, ma'am.
Done, Aleena?
Nearly, ma'am. Done, ma'am.
Okay. Coming to the thermodynamical parameters. So basically, we are going to talk about three parameters: pressure, volume, and temperature. Okay. So P is the pressure, V is for the volume, and T is the temperature. Now, what is this equation of state? So equation of state basically tells the relationship between these three. So what's the relationship? P, pressure, into V, volume, is equal to N R T. This is the equation. Ideal gas equation. So what is this? This is pressure. This is volume. What is N? N is the number of moles. R is the constant. So this is universal constant, universal gas constant. So value of it is 8.31314. And T is the temperature. So this equation we'll use in this chapter also. And thermal equilibrium I have discussed with you initially, if you remember, in the previous chapter. Basically, we discussed that when two bodies have different temperature, let's say this is having T1, this is having T2, and T2 is greater than T1. This temperature, this is hotter one, this is colder one. Or let's make it reverse. This is T1 is greater than T2. So some amount of heat will flow from body A to body B till the time temperature in A becomes equal to the temperature in B. This is the thermal equilibrium condition. So in thermodynamics, a system is in thermodynamical equilibrium if all the thermodynamical variables are constant. Means it should be in thermal equilibrium, the chemical equilibrium, mechanical equilibrium, or anything. Okay. Now, what is the law? What are the laws of thermodynamics? So the first law basically says that, see, this is an isothermal wall. Isothermal means conducting. Isothermal means the temperature can be exchanged. And this wall is adiabatic, means non-conducting, means matter, heat, anything cannot be exchanged here. So if I say temperature in A is equal to temperature in B, because of thermal equilibrium, some amount of heat will flow from A to B to make both of the bodies in equilibrium. They cannot exchange heat, but the orange one allows heat to be exchanged and the blue one doesn't allow. So A and B, they'll have the same temperature. Temperature in A is equal to temperature in C. Okay, this is also equal. Temperature in A and temperature in C, they will also become equal after some time. So this law says that if these two are in equilibrium with this is the common one. So temperature in B and temperature in C both will also be equal. Okay. So this is what is the zeroth law of thermodynamics. And regarding internal energy, the internal energy is the sum of kinetic energy plus the potential energy. But in ideal situation, we take the potential energy to be zero. So ultimately, your internal energy becomes a function of the kinetic energy. These are the points that you should know before coming and starting with the work done. All right, write it down from here. Thermodynamical parameters. Is it clear, Aleena?
Yes, ma'am.
Okay, write it.
Done, ma'am. Done, ma'am. Done, ma'am.
Okay, see, Aleena, coming to work done. So work done is basically related to the change in volume. So there is initial volume, that is V1. The final volume is V2. Okay, so work done is P delta V. This is the formula. Delta V means the change in the volume. V2 minus V1. This is the change in the volume. So pressure into change in the volume. This is the work done. So if pressure is constant, you're going to use this formula, means multiply pressure with the change in volume. And if it is variable, then you integrate it from V1 to V2. Like, look, this says that pressure of a gas is 10 pascals. Volume has changed from 5 to 25. What is the work done? So see, change in volume will be 25 minus 5. That will be 20 meter cube, right? And pressure is given as 10 pascals. So here work done will simply be 10 into 20, which will be 200. Remember the unit, joules. And there is one more question. Now see, pressure is given as 3V. Means this is variable. It is not constant. It is depending on time. So what we do, we use this formula, work done P dV integrating from 1 to 3. Now, instead of pressure, I'm writing this 3V dV integrate 1 to 3. Now, see, this 3 will be taken out. The constant V will become V square by 2 from 1 to 3. Right? This will be V square by 2. So this becomes 3 by 2. 3 square minus 1 square. I've put the limits. So I hope you remember this integration part. So this is 9. This is 9 minus 1, which is 8. So 3 into 8 by 2. This is 4, which is 12 joules. Like this. Now, when you're calculating the PV diagram means the graph between pressure and volume. Okay, PV diagram, whenever we use, it's the graph between the pressure and volume. So it is inversely proportional pressure and volume. So you always take the area under the graph like this. See, we take and consider this area. If expansion is done, then work done is positive. If compression is done, then work done is negative. And if the cycle is moving clockwise, then the work done is positive. And if it is moving anti-clockwise, it is negative. Like, look here. This is a graph given between pressure and volume. 5 and 10. These are the 2 points. So what we take? We take the area under the graph. What will be the area? Area is of a triangle. So half into base 10 into height 5. So we get 25. And see, this arrow is showing that this is the volume is increasing. It is expanding. So we take positive. And what is a cyclic process? Cyclic process is one which returns to its initial position. See, from A to B, back to A. This is what is called as a cyclic process. Like it is going from A to B to C to A. Now, in a cyclic process, we calculate again the area under the graph. Only like, look, this, if you get such graphs where you have the initial point, see, it is moving. So here we don't see expansion and compression. Here we will see clockwise or anti-clockwise because it's a cycle. So you'll be able to identify cyclic. See, whenever you have any graphs between pressure and volume, take the area. This is a rectangle. So length, that is 10 into breadth, which is 20. You get 200 joules. Now look, this is moving anti-clockwise. Look at the arrows. So we put negative. That's how you have to calculate. Did you understand this work done part, Aleena?
Yes, ma'am.
Okay, take the screenshot because your time is almost up. Please just take the screenshot. I'm scrolling it.
Done, ma'am. Done, ma'am. Done, ma'am. Done, ma'am. Done, ma'am.
Done, Aleena?
Yes, ma'am.
Okay, so in the next class, just write down the work done part. I'll start with the first law of thermodynamics. Okay?
Okay, ma'am.
Which
Yes, ma'am.
involves work done also. So get the work done part revised, this part, write it, so you will revise it by yourself. All right,
Yes.
you can leave now. Thank you.
Thank you, ma'am. Bye, ma'am.